So let us now look at something called a multi-component diffusion equation, diffusion coefficient. Right. What we did originally was to get Fick's law applied to a binary mixture, where we notice that you have something called a binary diffusion coefficient, that is a diffusion coefficient that is valid for a pair of species, and then we now switched into a multi-component mixture where we wanted to look at how the diffusion happens in a situation where we have lots of species. And now we came up with a monstrous equation the other day, which under some conditions might begin to look like Fick's law, let us say for example again for a binary mixture. But what we noticed was even in the presence of multiple species, the role of the binary diffusion coefficient was still there. That is to say, we were still looking at mixing happening between a pair of species at a time, right. So if you now had like 3 species A, B, C, then we were looking at a DAB, DBC and a DCA, okay. So we are now 3 binary diffusion coefficients for each pair of species that's involved there. But many times when you are now looking at let us say tens or hundreds of species, then we now have to worry about binary diffusion coefficients of each of the species with each other species, right. So that becomes a little bit more complicated, and it is not quite amenable to further simplification. For example, when we now did the multi-component diffusion equation, we could reduce it to Fick's law for the case of a binary mixture, okay, by making lots of simplifications in trying to justify disregarding the 3 other terms and to look for only the first term that contributes to this, and then we could see okay Fick's law is retrieved. But the question is, if we had a truly multi-component mixture, could we even think about something like a Fick's law, something as simple as a Fick's law, right. And for this the binary diffusion coefficient is going to be a bit painful to deal with, because we are now saying that you have to have a DAB times gradient YA, DBC times gradient YB and so on, and these binary diffusion coefficients are not going to be the same, right. So therefore many times it is worthwhile to think about what is called the multi-component diffusion coefficient. This is not the reality, okay. The binary diffusion coefficients are the reality, whereas we will now think about a multi-component diffusion coefficient artificially used. To relate diffusion velocities as a function of linear combination of concentration gradients. Right. So the way we want to do this is, so commonly we approximate as let us say yi vi vector is equal to minus di gradient yi, I equals 1 to n of course, or we should also be able to say xi vi vector is equal to di gradient xi, right. We have seen this before for a binary mixture. Like for example, if I now multiplied both sides by rho, the mixed density, then I get rho I vi vector is equal to minus rho di gradient yi. Previously we have done this only for a binary mixture, so if you were to apply this to a species A, then we would have a dAB. So that has two subscripts to denote that this D is valid for a pair of species A and B, but now we are looking at a multi-component mixture. That means you have more than two species, but we are having only one subscript. That is to say, we now want to tag the diffusion coefficient only to one species, much like how its Cp or maybe thermal conductivity or any of those quantities would be. That does not make sense honestly, because as we said, if some species has to mix into another species, you need to have the other species involved in this process, right. So dAB made sense because it was actually for a pair of species that way, but di, how can you have a diffusion coefficient that depends only on one species? The answer in this situation is, as I said, it's a bit artificial, but it's not too artificial, okay, because what we could now think about is how is this species, how is one particular species in a mixture mixing relative to, let us say, a species that is abundantly present in the mixture. Let us now begin to think about how each of the species in the mixture is going to mix with a one species that is the most abundant in the mixture, right. So typically in combustion applications, we are now looking at like fuel air mixtures, right. In air you have a lot of nitrogen that is pretty much sitting there, and that is like an abundant species around. So if it is now possible for us to think about how each of the species, like the fuel or the intermediates, the products, or the oxidizer air, the oxygen that is, and so on, mix with nitrogen, okay, and that is just present like a reservoir, and it did not matter to nitrogen or the abundant species how well it mixed with the individual species, it is not going to get affected because it is available in abundance, right. When that is the case, then it is possible for us to still think about the diffusion happening for a pair of species as opposed to tagging it to only one particular species, but we achieve the goal of thinking about only one species. You simply do not worry about the abundant species, right. So so the way we typically do this is this is valid, this is valid when one species is in large concentration and others are in trace. Now typically trace is a word that is used for something that is very, very small, okay. So it is sort of like an exaggeration that we are trying to do here in saying that when we are now having most species that are present in nominal quantities, not negligible, not in abundance, we cannot really say trace, but you get the idea that this is strictly speaking valid when one of them is in large concentrations, the other in trace, but we will now go ahead and say, well, we will identify an abundant species, the other ones are not going to be in trace, but we will still go with this idea, right. Okay, so then what happens? Generally we then use di is now considered identical to what is called as din, okay. That is as if we are now looking at a binary diffusion coefficient of each of the species relative to the abundant species, okay, and this you can now say is generally written as 1 minus xi divided by sigma j equals 1 to n and j unequal to I xj divided by dij. So that means we are actually using the dij information for all the species, okay, in the mixture in evaluating the what we call now as the multi-component diffusion coefficient, okay. Strictly speaking, this derivation can be possible only if you make an assumption that all the species are having equal velocities, whereas we would ignore that if we have to apply this to a situation where that is not the case, and that is in general not the case, alright. So that there is an assumption that goes with it which we normally violate. In addition, there is also one more caveat that we have to use, which is use this for n-1 species, okay, and obtain dn, okay, as follows. The reason why we can't use this for all the n species is if you were to use something like this and therefore get something like this and then plug it in your species conservation equations and add, strictly speaking we can't set the summation of all these diffusion mass fluxes to 0, okay. So it's sort of like it sort of violates mass conservation. Therefore, strictly speaking, if you are going to use this kind of a multi-component diffusion coefficient and correspondingly your relationship between the diffusion velocity for the species and its concentration gradient can be expressed as simply like a fixed law, okay. That is what we are trying to do. We are trying to get this form for relating your VI's to gradient YI's, or VI stars I should say, to gradient XI's, right. So if you have to do this, then don't do this for all the n species, okay. The nth species has to be obtained from adopting sigma yi vi vector is equal to 0, I equals 1 to n, and sigma I equals 1 to n yi equal to 1, okay. Use these to obtain your dn as sigma j unequal to n dj gradient yj divided by sigma j unequal to n gradient yj. But many times again, just as we ignore the assumption that is involved here in saying that the velocities of all the species is are equal, we also many times ignore this, that we just say let us not worry about the nth multi-component diffusion coefficient being obtained this way, provided all the n-1 diffusion coefficients are obtained this way, okay. You see that these are actually the multi-component diffusion coefficients that are obtained, okay. So this is ignored many times, okay. Okay, let us now move on. What we have done so far in trying to look at conservation equations in general for a reacting flow system of truly multi-component mixture is to derive the species conservation equation. Okay, we did this for a binary mixture, we now expanded it for a multi-component mixture. Then we noticed that we need to have a closure for capital VI vector, for which we wrote the multi-component diffusion equation and then looked at what are all the situations by which you could simplify this, and we have got to this point. Okay, and we also noticed that as you now add up the species conservation equation, all the species conservation equations, you will now get your overall continuity equation for the mixture as if it was a non-reacting single species case, right. We have not shown this in these lectures for the multi-component species conservation equation, but that I would like to leave it as an exercise for you to go back, look at the multi-component species conservation equations and then add them up to show that even for a truly multi-component system you should get the overall continuity equation to be like a single species non-reacting situation. Alright, so that means we have in our kitty the species conservation equation and the overall continuity equation. These are the two things that we have. Okay, and of course we also have the multi-component diffusion equation. So far we could now count the number of unknowns in our minds. Density, for example, density of the mixture is one of the unknowns. The corresponding equation that you can think about is like the overall continuity equation, right. And then you have a mixture velocity, the mass averaged mixture velocity that is showing up in the overall continuity equation, that is an unknown for which typically we resort to the momentum equation for the mixture, right, which is what we would now go ahead and do. And then we have the mass fraction as an unknown yi for I equals 1 to n, for which we now have species conservation equations 1 to n species conservation equations, which in turn shows up capital VI, for which we have the multi-component diffusion equation, okay, or its simplifications or many derivatives, which ultimately leads to something like a fixed law. But if you do not want to do the simplifications, you want to deal with the multi-component equation in all its complexity, then keep in mind that you have a xi showing up there. It is an equation for grad xi rather than for yi, which is your unknown in your list. Therefore you need to now use n equations that relate xi and yi. Okay, so as and when you now come across unknowns, you have to start thinking about corresponding equations to solve. Okay, so in this list so far, of course Wi contains temperature, for which we will have to resort to the energy balance. Okay, and then we will find that the momentum equation involves pressure, for which we also have to look at the equation of state. So that will completely close the system of equations. So in what we have looked for so far, we have not listed the mixture momentum, mixture energy and mixture equation of state. These three are yet to be done. So let us now do that. So momentum equation, I am just going to write it out, I am not going to do anything to derive this, and I am going to adopt the tensor index notation to do this in tensor index notation rho times Vj dou Vj by dou Vi by dou Xj plus dou Vi over dou T is equal to minus dou P over dou Xi Xj delta Ij plus dou by dou Xj of mu dou Vi over dou Xj plus dou Vj divided by dou Xi minus 2 by 3 mu dou Vk over dou xk delta ij close the brackets there plus Bi, where Bi is equal to rho times sigma k equals 1 to n yk fki. I am going to say a lot of things now, just say, I am not going to write it out. Okay. First, in tensor index notation, if you now have one subscript, that means we are looking at a vector. Okay. So for example, when you now say Bi, that is a vector, it is I goes from 1 to 3, 1 2 3, it will take index values 1 2 3 for three components in a 3-dimensional space. Okay. We can probably go a little bit backwards. Bi is actually rho times sigma k equals 1 to n yk fki, alright, and then of course rho does not depend on the summation, it could be taken in, and if you now were to think about rho yk as rho k fki, fki obviously is a vector, but k means it depends on species, right. So when have we seen a f corresponding, a small f corresponding to a species before? We did this not too far back, we probably did it like last class, or yeah, that's true. This is nothing but the body force per unit mass. Okay. So in this case it is going to be like the ith component of the kth species body force. Okay. So ith component of the body force per unit mass of the species k here. So it is sort of like acceleration, we went through this some time back. Okay. Times its density, it is going to mean that this is actually done per unit volume. Okay. This is a volumetric equation, this equation is now valid at a particular point on a per unit volume basis. That is the reason why we are multiplying by density, because this is actually per unit mass times density gives you per unit volume, alright. So fki is basically body force per unit mass, and therefore we now want to do this to plug it into this equation. So Bi then is like the net body force on the mixture, alright. This keeps in mind that the body force could be different for different species, okay, and this is because you are looking at like an electric field or a magnetic field that could be acting on different species differently and so on. Okay. Then I want to also point out that we have a summation over repeated indices in place. Okay. So if you now have like a Vj and Vj and Xj, then we have the sum over the repeated index. The remaining index will be I, which is the prevalent index in the entire equation. So this is for the ith component of a vector equation, as in this case for example you now see just that. The summation is in place over here as well, where delta ij is the Kronecker delta, and Kronecker delta stands for a value of 1 when I is equal to j and 0 when I is not equal to j. Therefore this basically will give you a gradient p. So what we used to write in vector notation as grad p needs to go through a complicated route over here, and this is first of all assuming that we are looking at a Newtonian fluid for the mixture, alright, and or rather we should say Stokesian fluid, okay, because it also has in place the Stokes hypothesis about the relationship between the linear viscosity and the bulk viscosity, and here dou Vk over dou Xk again has a repeated index summation over it, so that actually indicates a divergence of velocity, alright. So the divergence indicates a dilatation, and the minus 2 by 3 mu is the coefficient that comes out because of the bulk viscosity. So that is acting on the dilatation of the fluid. And of course for an incompressible fluid, dou Vk over dou xk will be equal to 0, the divergence is 0, that is actually coming from the overall continuity equation. If you sum up your overall continuity equation and recognize that the mixture is incompressible, then the density does not change with time, and the divergence of velocity will be equal to 0. So you should be able to get this, right. So in all these things we now are having to reckon with two more new things that we have not seen before. The first one is pressure, okay, and the second one is mu. Everything else is supposed to be counted as either an unknown or given. Unknowns that we have already counted are rho in the overall continuity equation, and Vi or Vj, whatever it is, in the overall continuity equation again. Yk is an unknown that is counted in the species conservation equation. Fki is supposed to be given to us, okay, on how individual species is being acted upon by body forces per unit mass of them. Therefore the thing that we do not know here is P, that's reckoned as an unknown, okay, whereas mu is a parameter in the problem, it's reckoned as a fluid property. The question is, we now have a mixture of fluids, okay, what mu do we take? Alright, so keep that in mind. We have a little problem here, okay, keep that in mind, and we will proceed. In fact, we are now continuing our search for more equations, because the species conservation equation had a Wi on the right hand side which had a temperature in the Arrhenius term, okay. So we want to now close for temperature, and for this we want to now look for the energy equation, okay. So and of course we now also have a pressure, and we will now have to close for that with the equation of state. We will do that next, but the next thing that we are going to do right now is the energy equation. The energy equation, just like the momentum equation, is also written for the mixture. That means we are not worried about energy of a particular species and so on. The only thing that we do that is species specific is the mass conservation for a particular species, okay, but rest of the things we do for the mixture as a whole. So the energy equation is also applied to the mixture. Now there are several ways in which you could write the energy equation, okay. So one of the maybe the mother of all equations would be to write out an equation for the stagnation enthalpy, because the stagnation enthalpy will take into account the kinetic energy involved in the motion of the mixture, and it will also involve the pressure work, because we would now say H is equal to E plus P by rho, okay, where E is the internal energy and P by rho is the pressure and density. You now look at a change in enthalpy, it also takes into account not only the internal energy change but also the pressure work term, and that is for the H, the enthalpy alone, okay. If you are now looking at H naught, which is H plus V squared over 2, then it also takes into account kinetic energy changes. So the mother of all equations probably should be to write in terms of the stagnation enthalpy. Now what I would like to point out here is that's overdoing things a little bit. The reason is, if you were to write your energy equation in terms of the stagnation enthalpy, keep it with you, and then you take a dot product of your momentum equation with velocity vector, which is, of course we are now looking at the mixture velocity, that is the mass averaged mixed velocity of the mixture. You take a dot product of, this is a vector equation, okay, so you now take a dot product of this equation with velocity, you now get this in dimensions of energy, okay, and that would be what is called as the mechanical energy equation. That means this equation then will only deal with the mechanical energy. This is the reason why in many PhD qualifying exams people may ask you something that you learnt in your undergraduate fluid mechanics. Is the Bernoulli's equation a statement of energy conservation or is it a statement of momentum conservation? The answer is both, right? You could conserve momentum or you could conserve mechanical energy. It is a matter of just taking a dot product of the momentum equation to get your mechanical energy, right. So in other words, if you are conserving momentum, it is amounting to conserving mechanical energy. What it does not do is to conserve the thermal energy, okay. So if you now obtained your mechanical energy and subtracted it from the energy equation written in terms of the stagnation enthalpy, then you get an energy equation that takes into account only the thermal energy conservation, okay. That is what we would do. We would just write out the equation for the thermal energy conservation. We will not worry about the stagnation enthalpy at all, right. So here we are, rho dH over dt equals minus gradient q vector plus q dot plus rho sigma capital K equals 1 to n yk fk vector dot vk vector plus phi plus dp over dt. Now I told you anytime you now look at an equation that keeps going on and on, okay, do not worry about it. You start looking at it term by term, okay, and then start making sense out of this. Capital D over dt, capital D over capital dt refers to the substantial derivative or material derivative or total derivative, right, which in turn would be like dou by dou t plus v dot del. That is the operator that we have to replace for this to look at the, this is essentially the inertial term in general, which can now be looked at in an Eulerian frame of reference as a unsteady term and a convective term together, right. Now if you were to derive this for yourself, you would understand that you got the divergence because this was actually a surface term in a arbitrary control volume. This is the way we actually got our species conservation equation derivation, okay. We had a surface mass flux across the control surface, okay, and then we applied the Gauss's divergence theorem to get a divergence. So whenever you have a divergence, you had to immediately think that this is actually coming from like a surface or from the sides, okay, and we will expand on this. Q dot is actually the, what do you think is Q dot? Let's just tease ourselves a little bit for a minute. What do you think is Q dot? Sorry? Energy supplied by what? External source? Damn, you knew the answer. What else could it have been? What are we looking for here? What are we looking for? Well, why are we here? Huh? Heat put into the reactor? Did he say put into the, why would I put into the reactor? I'm a combustion person, right? I want to get out something, right? I put in fuel and I want to get heat. So how many of you think that this Q dot is actually the heat that's coming out of the reactions? Like half hands up. Why? Or is the heat from the reactions hidden in here anywhere? This is the test of a combustion scientist or a student, I should say, right? Where is the heat released from chemical reactions present in this? We should probably ask this question at the end of explaining all the terms, but I can't wait. I mean, that's what I'm really looking for. Forget about everything else. In fact, I will forget about lots of those right. So some of these are basically written once and then we will say we will forget about this, but we can't forget the heat released from chemical reactions because that's our essence, right? Where is it in this? Is it the Q dot, right? The Q dot is essentially an external energy release rate term. So this is a is the heat release due to chemical reactions contained within your system, or is it to be externally put in, right? So you now take like a reactor or a combustor or whatever it is, and then you now put in your air and you put in your fuel, okay, and do we have to put in heat? No, right? Where was the heat contained that is now released? The H, where is it in the H? Standard what? The standard heats of formation of what? The products and the reactants, right? So this H is the mixture enthalpy, mixture specific enthalpy. Okay, so what's going to happen here is H is the mixture specific. The reason why we are multiplying by rho, specific means per unit mass, okay, specific enthalpy, and that is given by equal to sigma k, capital K equals 1 to n yk hk, where yk is the mass fraction still unknown, okay, in the system of equations, but hk is the specific enthalpy of species k. Okay. By the way, notice that we have shifted from A and B or I and J and all those things for species to a capital K, because if we now did this with the tensor index notation, we had I's and J's competing with us, okay. So we now use capital K for species from now on, yeah. So hk is the specific enthalpy of species K. That still doesn't show you the heat due to the chemical reactions, because you now further have to identify that hk is equal to delta hf naught k plus integral T ref to T cpk dt, small cpk dt. There are two things that I would like to point out in this. This is what is contributing to your heat release. This is not the full heat release, of course. This is only the standard heat of formation of the kth species. If you now plug this in here, you are now going to get a summation yk delta hfk. That is like saying I want to add up all the heats of formation of all the species that are involved in this mixture weighted by their mass fraction, okay. And keep in mind, it's the products that are going to have very high negative heats of formation. The reactants are not going to have that high negative heats of formation. They could have like small negative heats of formation, or 0 or close to 0, or small positive or positive or more positive heats of formation. All that stuff, that algebraic sum is like the net heat that we are going to get by thinking about a hypothetical process by which we broke down the reactants into reference elements by putting in some heat and then got the reference elements to form the products, right, and then get a lot more heat than what we put in, right. That's what is the heat release from the chemical reaction. So it's hidden in there. Okay. The other thing is we were actually writing this equation searching for temperature as an unknown, and look at where it is. That's in the sensible enthalpy term on the top of this integral. That's the unknown. Right. So okay, let's look at a few other terms. Let's look at grad Q, divergence Q, or what's Q first of all. So I told you it's coming from the surface. So this is heat flux. Okay, so this is heat flux. This is an energy rate equation. Okay, so this is actually per unit time. Whatever we are writing here is actually per unit time. Things are happening as they are happening. You are looking at what's happening per instant per unit time, right. And this is like heat flux. That means what's happening per unit time per square meter per unit area, right. So what is this heat flux? This is now going to be like equal to minus K grad T plus rho sigma capital K equals 1 to capital N HK YK capital VK vector plus or UT sigma I equals 1 to N sigma J equals 1 to N xj dt comma I divided by W capital WI dij times capital VI vector minus capital Vj vector plus QR vector. Clearly heat flux is a vector, okay, which is now going at an arbitrary direction. I shouldn't say arbitrary, it's going at a direction not exactly normal to a surface. It's having like a n vector, unit vector, unit normal vector that we have to take a component with respect to, and that's how you would get the Gauss's divergence theorem applied over there. And then there are about 1, 2, 3, 4 4 terms there. Okay, how did you get 4 terms? The first term minus K gradient T, what is it? That's a heat conduction. The heat conduction is actually coming from the sides from at a particular point, because you have a temperature gradient with respect to this point and the adjacent point, right. So if you had a hotter region on the side, you're now going to have heat into this point. If you're going to have a cooler region on the side, you're going to have heat away from this point, right. So that's the familiar Fourier law of heat conduction. So effectively we are assuming that we are looking at a Fourier fluid. That means a fluid that a heat conducting fluid that satisfies Fourier law, alright. But the fluid is actually a mixture of lots of species. Okay, so what is this K? It's a conductivity of the mixture, right. So similar to this mu being viscosity of the mixture. So we need to have an idea of how to deduce the conductivity of the mixture and the viscosity of the mixture for a mixture whose composition is yet to be solved for. Okay, so actually we don't know this, and this is changing from point to point and time to time, okay, in this mixture, because the composition is changing as we go from fuel air over here to lots of stuff and then finally some products and so on, okay. So I am not going to tell you how the mu and k depend on the species concentration instantaneously. I am going to put this out in a website with that this video will go with. It has to go to kinetic theory, okay. So we can't do this in the continuum framework. We will write out equations that give you this later on. What is this term? Can we carefully look at this? Okay, rho is out. You can take this in and then make this rho yk as rho k, hk, all right, capital Vk. As a matter of fact, so long as we had yk, hk, sigma, you would get back your h, okay. But then you had a capital Vk that prevents you from summing over only yk, hk, right. Yk is weighting the summation, sorry, Vk is weighting the summation. What is capital Vk? That is the diffusion velocity of species k, right. How did we get this term? The answer is, you see, when we were looking at this, we had a dou by dou t plus v dot del h. The v there is the mixture average, is the mass average velocity of the mixture, okay. And then keep in mind that h is sigma yk hk. The mass averaged velocity of the mixture is not species dependent, it is now a mixture property. So you could have pulled it out of a summation and kept your sigma yk hk as h, that is how you got your h, okay. But in reality, how is the enthalpy flowing into a point and getting out of that point? This looks like it is convection, right, in convection of enthalpy, but this is like convection of enthalpy of the mixture, okay. But in reality, whenever any matter moves, it carries with it mass, momentum and energy. That is the reason why we are able to do mass conservation, momentum conservation and energy conservation. Here we now have a bunch of species, each of which is carrying some mass, for which we did a species conservation equation at any particular point, okay. And then we had a mixture momentum conservation, all right. But if you are now thinking about the energy or the enthalpy that the species carries with it, okay. Now it carries with it enthalpy at its velocity, but what we have accounted for is like a overall enthalpy that the mixture carries at the mixture velocity. That is what this accounts for. Then there is a deficit. There is still enthalpy carried by individual species at its diffusion velocity with respect to a mixed fixed coordinate system, right. In reality it is carrying its enthalpy at its velocity, but then now we have taken like a mixture average, mass average velocity of the mixture, okay, and then that does not depend on species anymore. So we should now be able to add up a contribution of all the species put together in terms of an enthalpy to see how the enthalpy of the mixture gets convected, right. But then there was one more contribution that we forgot. There is like a diffusion velocity with which the enthalpy is still going, all right. That is coming up if you now have a mixed fixed coordinate system. That is what this is. So you now have a Vk times hk rho k, okay. So that is actually the enthalpy of the mixture that is due to diffusion, okay. So you got to keep that in mind. And then this is pretty interesting. This is what you would call as the Dufour effect, okay, where this is the opposite of the Soret effect that we saw the other day, okay, where there what we saw was if you now had a temperature gradient, it gave rise to a contribution to a concentration gradient. Here if you now have diffusion velocities, okay, which in turn are supposed to be functions of concentration gradients, it gives rise to a heat flux. Okay. So where you had a temperature gradient giving rise to a concentration gradient is called Soret effect, where you have a concentration gradient giving rise to a heat flux is called the Duffer effect. Okay. And you can clearly see that you have a dt comma I divided by dij showing up here as well, alright. So that is what is called as the Duffer effect, and finally QR is a radiation heat flux. So what we have had so far here is only the conductive heat flux, therefore you also have to add a radiation heat flux, and the radiation heat flux will have to be modeled based on Stefan's law, and if you have to look at an enclosure or something of that sort, you have to have these shape factors coming in and so on, absorptivities and emissivities and all those things. That is something that you want to do separately, but at the moment you just have to plug in but keep in mind that it is going to depend on temperature. Okay, so it has a T to the 4 expression, and that could be an unknown because temperature is an unknown. Okay, so you could plug in an expression for that if you want. We will stop here for now and then pick it up from here next week. We still have a few more terms to go. We want to know what this is, and so on. Okay, the energy equation takes some amount of energy.